Hello students. Students, in today's video, I am going to discuss the mechanism of nucleophilic substitution reactions of haloalkanes. So, without wasting any time, let us begin the video and explore mechanism of nucleophilic substitution reactions of haloalkanes. Mechanism of nucleophilic substitution reactions of haloalkanes. This reaction has been found to proceed by two different mechanisms, which will be discussed as substitution nucleophilic bimolecular SN2 and second substitution nucleophilic unimolecular SN1. Substitution nucleophilic bimolecular SN2 reaction. The reaction between CH3Cl and hydroxide ion to yield methanol and chloride ion follows second order kinetics, that is, the rate depends upon the concentration of both the reactants. OH minus nucleophile reacts with RX substrate, forms OHRX transition state, and then OHR product with X minus halide ion. In this, the solid phase represents the bond coming out the paper, dashed line going down the paper, and a straight line representing bond in the plane of the paper. The above reaction can be represented diagrammatically as shown in figure. Figure represents red ball represents the incoming hydroxide ion, and green ball represents the outgoing halide ion. It depicts a bimolecular nucleophilic substitution SN2 reaction. The incoming nucleophile interacts with alkyl halide, causing the carbon halide bond to break, and a new bond is formed between carbon and attacking nucleophile. Here it is a C single bond O bond formed between carbon and hydroxide ion. These two processes takes place simultaneously in a single step, and no intermediate is formed. As the reaction progresses and the bond between the incoming nucleophile and the carbon atom starts forming, the bond between carbon atom and leaving group weakens. As this happens, the three carbon hydrogen bonds of the substrate starts moving away from the attacking nucleophile. As a result, configuration is inverted. The configuration of carbon atom under attack inverts in much the same way as an umbrella is turned inside out when caught in a strong wind. This process is called as inversion of configuration. In the transition state, the carbon atom is simultaneously bonded to incoming nucleophile and the outgoing leaving group. Such structures are unstable and cannot be isolated. Thus, in the transition state, carbon is simultaneously bonded to 5 atoms. Configuration: spatial arrangement of functional groups around carbon is called its configuration. See the structure A and B given below carefully. There are the two structures of the same compound. They differ in spatial arrangement of functional groups attached to carbon. Structure A is mirror of structure B. We say configuration of carbon in structure A is mirror image of the configuration of carbon in structure B. Since this reaction requires the approach of the nucleophile to the carbon bearing the leaving group, the presence of bulky substituents on or near the carbon atom have a dramatic inhibiting effect of the simple alkyl halides. Methyl halides react most rapidly in SN2 reactions because there are only 3 small hydrogen atoms. Tertiary halides are the least reactive because bulky groups hinder the approaching nucleophiles. Thus, the order of reactivity followed is primary halide, secondary halide, tertiary halide. The figure shows steric effects in SN2 reaction. The relative rate of SN2 reaction is given in parenthesis. In the year 1937, Edward Davis Hughes and Sir Christopher Ingold proposed a mechanism for an SN2 reaction. Hughes worked under Ingold and earned a BSc degree from the University of London. Substitution nucleophilic unimolecular SN1. SN1 reactions are generally carried out in polar protic solvents like water, alcohol, acetic acid, etc. The reaction between tertiary butyl bromide and hydroxide ion yield tertiary butyl alcohol and follows the first order kinetics. That is, the rate of reaction depends upon the concentration of only one reactant, which is tertiary butyl bromide. CH3 whole thrice CBr reacts with nucleophile hydroxide ion, gives CH3 whole thrice COH with Br minus ion. It occurs in 2 steps. In step 1, the polarized C single bond Br bond undergoes slow cleavage to produce a carbocation and a bromide ion. The carbocation thus formed is then attacked by nucleophile in step 2 to complete the substitution reaction. In step 1, CH3 whole thrice CBr form slowly CH3 whole thrice C plus cation with Br minus ion, and then CH3 whole thrice C cation reacts with strong nucleophile OH minus, and in step 2 gives CH3 whole thrice C OH. Step 1 is the slowest and reversible. It involves the C single bond Br bond breaking, for which the energy is obtained through solvation of halide ion with the proton or protic solvent. Since the rate of reaction depends upon the slowest step, the rate of reaction depends only the concentration of alkyl halide and not on the concentration of hydroxide ion. Further, greater the stability of carbocation, greater will be its ease of formation from alkyl halide, and faster will be the rate of reaction. In case of alkyl halides, 3-degree alkyl halides undergo SN1 reaction very fast because of the high stability of 3-degree carbocations. We can sum up the order of reactivity of alkyl halides towards SN1 and SN2 reactions as follows. For SN2 reaction, CH3X primary halide, secondary halide, then tertiary halide. And for SN1 reaction, CH3X primary halide, secondary halide, then tertiary. CH3X is slowest and tertiary fastest. Allylic and benzylic halides so high reactivity towards the SN1 reaction. The carbocation thus formed gets stabilized through resonance. For a given alkyl group, the reactivity of the halide Rx follows the same order in both of the mechanisms Ri, Rbr, Rcl, and Rf. Students, through today's video, you have just learned mechanism of nucleophilic substitution, reactions of haloalkanes. I hope you enjoyed the video. So to keep receiving more videos from me, please like and subscribe to the channel and share it as widely as possible. That's all for now. See you in the next video.